Partial derivatives can be extracted from a number of sources. Often in experiments, what we'd have is a table of data rather than a formula for a function or a diagram like a contour diagram. But we can still work towards calculating or estimating the partial derivatives when all we have is a table of data. So we're going to consider a function here, which is a function of x and a function of y, and we're going to consider the point 1, 0. Sorry, 1, 1. 1.0 in this direction. That didn't work. And 1.0 in this direction. There we go. We can find out some basic properties right off the bat. Like f of 1, 1 is the value we see in the table here, 7.39. But we're interested now in derivatives of that function. So the derivative of f with respect to x at that point and the derivative of f with respect to y. And what we're going to do here is take advantage of this approximate idea or the limit idea of a partial derivative, that the derivative is approximately the change in the function divided by a small change in x. And in this particular scenario, one of the ways we could do that or estimate that value is to take 2 points which differ in, these different y values. That wouldn't make any sense in this case here. We need 2 values that differ in x coordinate, x going from 1 to 1.1. If we take these 2 points, let's take the second minus the first. So 5.99 minus 7.39 are the 2 f values. The x values are 1.1 and 1. So we have a nice positive delta x here, but the value of the derivative in the other direction ends up being negative because the difference here is negative. We end up with negative 1.4 over 0.1, and that is negative 14. And so what that tells us is, as we take a step to the right, at least from this point, we would go down by 14 roughly every full unit step. And remember, these are steps of just 0.1, so a full unit step would be 10 of these steps. And that seems not unreasonable because we went down by 1.4 in the first step here. Do that 10 times, we'd go down by roughly 14. The key thing for the calculation, though, is this association again between the derivative concept and its idea as a slope being calculated by a rise over run or a change in f over a change in x. We can do exactly the same thing with the y. We can say that the derivative of f with respect to y is going to be approximately a change in f divided by, again, a small change in y. That'll be our best guess. This time, we'll take 2 points that differ in their y values but have the same x coordinate. So that same idea as before of vary only the variable you're differentiating with respect to, all the other ones should stay constant. And if we do that here, we're going to get a 9.97 minus 7.39. So second point minus the first. And as long as you do it consistently, you don't have to even do it that direction. But this makes a nice positive delta y here. And if we do that and do our calculations, we get 2.58 over 0.1, and that is 25.8 overall. And so what that again tells us is this small step, a step of 0.1, raised our function value by 2.58. If we were to do that more regularly, the rise would be 25.8 for the function for every single step in y. Again, assuming that was a small step overall. So that's one way to estimate the values. Hopefully, you are asking yourself, why did we pick these two here? Why not pick the x before the 1.0? You can absolutely do that. There are multiple answers that are possible, and in fact, there's a whole study in numerical analysis of which particular estimate is the most reliable most often. And there's lots of different choices there. They all involve the points that are closest to 1, though. That's the key thing, is we still want a small delta x or a delta y, but the details of which particular combination of points that we pick to get these deltas turns out not to be that crucial unless we're super interested in super accuracy, but there still are choices right now that we could make and get reasonable estimates. The last thing we might want to interpret here is going back to the graph. Well, we found out that the x derivative was negative 14, so f decreases as x increases, and this would be near the 0.11. That's probably true in a region around it. We won't get fussy about where that region is, but there will be a region around that point where f is going to go down every time we take a step towards positive x's. And likewise, this positive partial derivative here means that as y increases, the function is going to increase as well. Again, that applies near the 0.11 where these calculations were based.